Okay, let's see what's working. So, starting, I hope, whoops, causing problems, something. So, how do you like my blackboard? So what I'm calling segment 1.1, and if you look at the progression of the notes, I have a whole part 1 which is all prerequisites. So at some point you should have seen it at least once and maybe many, many times. But so we're going to look at and recall some of those things. And other places it might be prerequisite material, but with a different slant than you've had before too. So, but go back and review exponents. So you start out by learning exponents as what? A shorthand method of listing factors. So if you have the same factor many times in a product, it's just shorthand for that, isn't it? So that's why you start with exponents. Of course, you can sometimes compute that as a number or simplify it in different ways. So you learn about exponents starting in that fashion. Now, if you look at a progression of exponents of, say, 3 in this case, you progress by throwing in one more factor of 3 each time. But if you progress the other way, starting maybe at 4 factors of 3 and move backwards, what do you have to do? Well, instead of multiplying, you divide. So if I take this last one and divide by 3, where do I end up? So 1. And so in that case you would, well, let's see, that would be 1 less factor, so that would be 0. So if I take the definition that you first start with exponents and run it backwards by dividing by 3, it tells you what 3 to the 0 should be, right? And if you back it up again, then what do you get? Well, 1 less would be minus 1 factors, but that should be what? Divide 1 by 3 and get a third, wouldn't you? And so you can take the basic definition you might learn in first grade or somewhere. And if you run it backwards by dividing by 3 instead of adding a factor of 3, you get, what, 3 to the 0, 3 to the minus 1, 3 to the minus 2, and other things like 3 to the minus 4 should be 1 over, well, divide by 3 4 times, right? So it gives you that relationship between negative exponents and positive exponents, reciprocals. So if you take basic exponents, if you follow that progression with any number, the 0 power is going to have to be 1. Now you have to make a little thing here. It doesn't make sense with 0, but any other number. So if we have an exponent 0, the answer is 1. If we have an exponent that's a minus, it's what? The reciprocal without the minus. If you multiply two of these creatures, okay, so you're putting together so many factors and so many more factors, so altogether you should have n plus m factors. So if you just look at factors of 3, like 3 squared times 3 cubed. You list 2 of them, you list 3 of them, so altogether 5 of them, right? So that's all that rule says. And a similar thing happens if you divide. So if you throw away a bunch of factors, what are you doing? Subtracting the exponent? So simplifying products have the same factor with exponents. You can add or subtract. There's also sort of a distributive rule for products and exponents, is that this exponent of an entire set of factors can be written as separate factors with exponents. So 3x as a base set of factors to the 4th power is the same as 3 to the 4th power times x to the 4th power. So that's a review of the basic properties of exponents. There's some terminology. That entire quantity, something like 3 to the 4th, is said to be the 4th power of 3. So the entire quantity is referred to as a power that has what? An exponent. And a base. Now, all of those rules, we sort of develop them with nice positive whole numbers a lot of times. But it's actually true for all real numbers. Well, when things are defined, I should say. So you can make sense out of things like 3.6 to the power 1.89. Now, it's a little hard to list 1.89 factors of 3.6. So really can't think of it that way. But the rules, whatever that is, the rules of exponents apply. So if we multiplied this times 3.6 to the 1.01, we could combine that as 3.6 to the 2.90. So the exponent rule still works. Add the exponents, right, if the base is the same. Did I add correctly?
You're doing great.
Oh, not too good at arithmetic. I learned arithmetic when I was in graduate school, and I worked at a restaurant where you had to do they didn't give you time to use the cash register, so you had to compute everything in your head and then give it to them. So at that point, I learned arithmetic. So you know the exponent rules, you kind of remember, but just kind of recall them, and the fact that they work for any numbers. And I sort of said on the side, when things are defined, because a few things don't make sense, like the square root of minus 3 is not a real number, so, or minus 3 to certain powers don't work. So in many cases, we kind of have to restrict ourselves to non-negative numbers when we write these things. So, well, we can begin to make sense out of these 1.89 factors because they come from what are actually roots. So, if I write the square root of 4, well, what's your answer? So you know about those, right? Of course, you don't think about it, but there's always the possibility of the minus 2, isn't there? But when you write this particular notation, oh, pen is lagging. Come on. Yeah, then so, using the radical notation for the square root, usually if you don't put a sign, you mean the positive root. And when you have a choice in that notation, you would put the minus square root of 4. Oops. And then, I have to. Sometimes it's the way I hold the pad, and I'm pushing on something underneath or something. Things like cube root of 27. Do you have an answer for that? Yeah. So you know about roots, right? Of course, this is the cube root, so is there a minus 3 as an alternative? No. So some things have more than one answer, some things don't as far as roots go. And square root minus 4, what's your answer? NA or something, right? At least if a real number doesn't exist. So we're going to sort of avoid complex numbers. But cube root, there is an answer, right? So, and that's what I was referring to. All these rules work as long as things are defined. So we're not going to try to apply rules sometimes to a minus 4 and other times we might, right? So cube root of minus 4 makes sense as some number, but square root of minus 4 doesn't. Now, all of a sudden I brought in these roots and radicals. Now that'll work. Sorry. Come on. Talking to the computer always helps. If I write square root of 2 and I multiply times the square root of 2, then what's the answer? Because that's supposed to be what the square root of 2 means, right? The number that you would square to get 2. Now, if I write 2 to the 1/2 and 2 to the 1/2, and I do exponent rules, this would be 2 to what exponent? Supposed to add the exponents? So, to make the exponent rules work, 2 to the 1/2 squared is 2, but square root of 2 is also the same thing, isn't it? So square root of 2 and 2 to the 1/2 power are exactly the same thing. And so in that way we get like 0.8 and 0.89 as possible exponents. General rule would be that x with an exponent of 1 over n is just another way to say the nth root. So exponent 1/2 is a square root. 1/3 is what? Cube root. The 1/4 is the 4th root, and so forth. So we have radical forms and we have exponential forms. Okay. Oh, now, this is also a place where you start making quick errors when you're doing computations, because we have 1 over n, and we have 1 over x to the n. Both of them having fractions, right? And so don't accidentally use one rule for the other. So fraction in the exponent refers to a root. Whoops, not the cube root necessarily. Fraction of the power refers to what? Reciprocals and negative exponents. Okay. Oops, maybe I should stay in a different place. So I don't like to be back there. And if you keep moving back, see, I can move with you. Doesn't work like in church where you can sit in the back pew. I'll just go back there. So 2 rules, if you look at them as they go through, makes sense, but a place where they both have fractions in the rules, and I'll see little mistakes on homework and tests where you mix the 2 up. Because you do a quick thing with the fraction, and so you use the root where you should have had the, negative exponent reciprocal, and vice versa. So be conscious of those little places. Now, another rule, come on, let's figure out what's going on. Let me get a whole new page here. There we go. I sort of did this in one instance, but I didn't do what? A power of a power. In that case, you get the exponent simplified would be a product. So if you multiply 2 powers, you add the exponents. If you take a power of a power, you're going to multiply the exponents. So if I had 3 squared cubed, then it's 3 to the 6th power. And so that allows me to look at things like, well, what's 3 to the 4/3 power? Well, if I use this rule the other way, it's 3 to the 1/3 to the 4th. or the cube root of 3, and then fourth power of that. So if you can come up with the cube root of 3, then you can take the fourth power and you have what that means. So in that sense, you can define any exponent. Fractional exponents. Oops, come on. Decimal exponents, if you end the decimal, well, it's some fraction, isn't it? So it's actually 3 halves, isn't it, that one? So you get 3 square roots of 3. But 2 of those make what, 3? Whoops. Maybe. Somewhere I'll get this right. Let's see. Maybe it would help. Where's my eraser? There we go. So in radical form, we would think of simplified as 3 square root of 3 instead of square root of 3 cubed. It's a little different in exponential form. We tend to think of, the first one as simplified. 1 base, 1 exponent. So we sort of do things in different forms depending on radical or exponential form. So here, instead of writing cube root of 3 to the 4th, or cubed, square root of 3 cubed, we write on the outside of the radical anything possible, right? So with exponents, we have the choice of the exponential form or the radical form. And so either one can be useful. Converting to one and then back can be useful in the middle of a problem, depending on what you want. Now, now the base or the exponent may be more than a single label expression. So we've sort of dealt with that somewhat with the exponent, because if you have a sum, you could break it apart and differences. But what happens with the base? Well, in this case, you might have dealt with polynomials, so you could actually square and take the 4th power, but that's not the idea of this particular presentation. And I don't want to take the time to do that. But you could simplify this in terms of how many factors, couldn't you? As long as the base is the same, you can put them together with a single exponent. So instead of listing 2 factors and 4, I could just list it as 6 of those. Of course, the other rules of exponents apply. So I had the same factor and I divided. I would subtract the exponents and end up with a -2. Now, for my preference, I don't really care whether you end up with negative exponents or positive exponents. So that's a good simplified answer as, if you prefer, positive exponents and write this as the reciprocal, that's fine, either way. Because when you look at the textbook, they may prefer one way over the other, so just have to deal with that. Now, the top one and the final form of the bottom one, you might be tempted to multiply out to get some long polynomial. I guess the bottom one isn't too bad, it's a square. In general, it's not a good idea to multiply out factors, unless you have to, because factored form is always better, because it's not impossible to multiply things out. It's a pretty standard progression, right, no matter what the factors are. But it can be very difficult to factor expressions, right? So you would prefer to have the factored form. So keep things factored, that would be my advice, until you absolutely have to multiply them out. So, a little review of exponents. And we're calling that the radical forms and roots can actually be written as exponents. But